If you took away the x and y coordinate lines, every graph we've seen so far would look like this, or perhaps like one of these. Every graph has been a straight line because the equations we've graphed have all been what we call linear, straight line, or first-degree equations. Lots of x's, many y's, but not an x squared or y squared in the whole bunch. Pretty simple stuff, but exactly what we need when we want to get a picture of a single equation like this one. You remember how we did that. The whole trick here was to pick a value for either x or y and then solve for the other unknown by substituting in the equation. If we pick 0 as the value of x, we find by substitution that y equals 7 over 3. Then we pick y as 0, and we find x equal to 7 over 2. You'll recall that we often chose 0 as our value because when we went to graph the equation, our 0 values for x and y became our x and y intercepts. Very convenient. But any 2 points would give us the same line, of course. And plotting any third point would confirm our answer by landing right on the line. If it didn't, we knew that we blew it somewhere. If you need more review than that, you'd better check those modules on graphing straight lines. What it all comes down to, though, is this. We've been looking at graphs where as x went marching from 1 to 2 to 3 to 4, y went 2, 4, 6, 8, or maybe 3, 6, 9, 12. But anyhow, something simple, direct, and easy to predict like that. Now we're going to look at equations where some very different things happen. No more first degree, no more straight line, no more linear equation. So how do we handle something like y equals x squared? New question. Same old answer. Choose some values, substitute, plot some points. We pick a set of values for x. Find the value of y for each value of x, and plot the points. 0, 0, 1, 1, negative 1, 1, 2, 4, and 3, 9. On a graph, they look like this, and we see instantly that we're into something new. There's no way a straight line is going to connect these points. We need something else. The nice smooth curve we call a parabola. Actually, the term parabola covers a lot of ground because parabolas come in so many different sizes and shapes, and they can be located anywhere on the Cartesian plane. But here's one thing you can hang on to: a model equation. An equation of this form will, in general, give us a graph that is a parabola. Understand, of course, that A, B, and C are the coefficients here. They stand for numbers. If we approach this equation right and treat it gently, it can tell us lots of things about graphing quadratic functions. So we're going to spend the rest of this module asking 3 questions about the equation, one for each of the 3 terms, ax squared, bx, and c, but not in that order. We'll switch the last 2. First question. Take y equals ax squared as an equation all by itself. The question: what happens when we use different values for a? Different coefficients, different numbers, like this. Y equals 1x squared, y equals 2x squared, y equals 3x squared. How does the difference show in the graph, in the parabola? The answer: we work out tables of values for each of the 3 equations, we plot the points, draw the lines, and we come up with three different parabolas which touch each other only at the origin, point 0, 0. Y equals 1x squared produces the lowest, broadest, and flattest curve. As we go to the higher coefficients, 2x squared and 3x squared, the parabolas grow steeper and narrower, hugging closer and closer to the vertical axis. So that's our answer. The higher the x squared coefficient, the narrower the curve. Now, still on the first question, what if we replace y equals x squared with y equals negative x squared? We choose some values of x, and you can see what happens to y. It's all negative. So the equation y equals negative x squared just takes the curve for positive x squared and turns it upside down. Y equals negative x squared shows up entirely at the bottom of our coordinate plane. And if we looked at negative 2x squared and negative 3x squared, we'd find them hugging the vertical axis at the bottom, just as we saw them doing on top when we used positive values. That tells us all about A in our general equation. The second question is about C. So let's make another equation, and this time we'll include a value for C, along with a plain old 1x squared. This one's all yours. Y equals x squared plus 3. Go ahead and work out some points for it now. Plot the points and see what your parabola looks like. As usual, I want to pick some values for x and substitute each one in the equation to find the corresponding y. That defines a set of points for me. You may have chosen different points, but they should lie along the same smooth curve that looks like this. Now for that second question. What is the difference between y equals x squared and y equals x squared plus 3? The answer? Plus 3 adds a plus 3 to the graph, just as it says. It slides the curve upward by 3 places. And if you think another positive or negative number, y equals x squared plus 2, y equals x squared minus 6, would move the whole curve up 2 places from 0 or down 6 places from 0, you're right. In fact, by now you should be able to picture, at least in general, what all of these parabolas would look like. See if you can plot them in your mind before I show them to you all at once on the same coordinate plane. I know you're expecting the answers right now, but first I want you to think about what causes these shapes. Which two equations are the same, but one positive, the other negative? Which three graphs are identical except for sliding up and down the y-axis? And what makes them do that? Ready? Here's what you're looking for. Positive and negative x squared are mirror images of each other. And the other three are the same curve, at 0, up 5 from 0, and down 6 from 0. to reflect the plus 5 and minus 6 in the equations. So in answering our first question, we learned that the steeper curves go with the higher values for A. Our second question told us that the value of C makes the whole parabola slide along the vertical axis. Now go back to that general equation for a moment, and we have our final question. What if we add an x term to our equation? What will it do to our graph? To find out, we take an example and graph it. We choose x values, substitute in the equation, which takes a little longer this time because the equation is longer, and come up with a set of xy coordinates to plot our curve. 0, -6, 1, -6, -1, -4, and so forth. We expect to see something different. And we do. Can you see it? The whole curve has moved to the right, or we could say it's no longer symmetrical around the y-axis. There is more of it on the right than on the left. And of course, it's also moved down from the origin because of the -6. Now let me exaggerate the same picture a little and give you a useful label. The roots are the 2 points where the graph crosses the x-axis, just like x-intercepts. To find the roots in a particular equation, like the one we just saw, for example, just give y a value of 0 and solve the equation. Here I've switched the two sides because we're used to having the 0 on the right when we solve a quadratic equation like this. To solve for x, we can factor out to x minus 3 and x plus 2. So x equals a positive 3 or a negative 2 when y equals 0. And we found our two roots, -2, +3. If you needed any proof of that, you already had it on the graph, because we saw a moment ago that -2 and +3 were exactly the points where the graph of x squared minus x minus 6 crossed the x-axis. Usually, of course, we find the roots first, and then use them to help us graph the equation. Try that now on this one. Find the roots, then plot a few other points, graph the equation, and then come back and we'll compare notes. First, I pick a value of 0 for y, and I put the 0 on the right where I'm used to seeing it. I check for factors and find happily that the equation factors out to x plus 3 times x minus 1 equals 0, which tells me that the two roots are -3 and +1. That's pretty easy. But please notice that sometimes you'll have to solve by another method, a quadratic formula or completing the square. And notice in passing that some parabolas have no roots. We've already seen a couple of those. Okay, I have the roots, -3 and 1. I need a few more points, so I also plot x equals 0 and x equals -1, which gives me the points 0, -3, and -1, -4. And a graph that should look just like your graph, whether you plotted the same points or not. I'm sure you've noticed that every one of these graphs has a vertex, a point where the curve turns around and starts going the other direction. The name vertex will come in handy. Remember it. It would also be handy to have a way to compute the vertex, but for that you'll have to wait until intermediate algebra for an answer and until calculus for the best answer. And that's pretty much it for this module and for this course. But let me point out a couple of other shapes you'll see in intermediate algebra, along with the kind of equation that produces them. A circle, an ellipse. One thing to notice is that these are all quadratic equations. A hyperbola. All these graphs are special examples of forms called conic sections, which were discovered by those clever Greeks a few thousand years ago. Conic section literally means cone cutting, because all these figures can be produced by taking a solid cone and slicing through it at different angles. And all the figures produced that way are described by quadratic equations. But for this course, enough. Congratulations, you've done it. If you need more information on quadratic graphs, you'll find it right where you expect to find it, along with enough examples to keep you busy until it's time to register for the next course. And won't it be great to know you're ready to move on? Good luck.